So in today's video, what I'm going to show you how to do is how to connect an Arduino to a display and connect it to Microsoft Flight Simulator through Axis and O's. And obviously that sounds like a big project, and in some ways it is. But I'll provide you all the information you need to make the project happen, although this isn't a tutorial on how to program an Arduino, so I'll provide the code. There's a GitHub link in the description below that you can use and get the code, and you might be able to get away with just changing the Wi-Fi information in there for it to connect if you did everything basically the same as what I do in this project. There's a Fusion project also for the 3D model of an example, and I'll show it in a little bit. But this isn't really a tutorial on how to use Fusion either. I mean, both of those topics are, video series in their own right. But if you have some understanding of those topics, then this might be enough to get you going, so that way you can create your own. So let's start with the demonstration video here. You can see the display in the bottom left, and I know I'm talking over a video that's playing in a video, so it's kind of complicated, but this is the best way I could figure out how to do it. So we have the instrument down below. This is a 2-inch display and connected to an Arduino that you can't see right now. And then up here to the upper right is a Pilatus PC12 altimeter. And so let's get this started, and we'll talk about what you're seeing. So it's connected and it's getting data. Right now I'm moving the altimeter bug, and the PC12 has a altimeter bug also. I'll talk more about that later, but you can see how that was moving. Down below you can see the barometric pressure changing. It's at 330.02. And then I set it to standard pressure there, and you can see that the needle respond to those pressure changes. And so it definitely works just like the altimeter does. It's really just pulling the data from the sim through Axis and O's. Now in the upper right, you can see me in the sim. I'm setting up the autopilot. I'm going to do a 1,500 foot per minute descent. I just engaged it. You can see the nose dip in the attitude indicator, and you can see the display changing here. And it pretty much matches what's in the sim. This is an F-18 style display because that's the kind of cockpit that I have. It's modified off of the Open Hornet design, so that's why I'm sticking with an F-18 look. Although the PC12 has a pretty cool altimeter, in my opinion. So let's start the conversation of how we put all these pieces together with Axis and O's. I've got the app open here on the screen, and the only thing that you really need to make sure is that the web service or its WebAPI can be connected to. And so underneath Tools, the Tools menu, is a Configure Web API port. When you click on that, you'll get a little window, and it'll show you what address that you would use to connect to it on your local network, and it'll show 2 port numbers that you can use to connect to it. Those 2 port numbers are kind of useful because he tells you that you can load balance between the two if you have a lot of devices connecting. At the moment, I'm only tested 1 device so far, so I've got probably 7 or 8 that I might end up doing here in the cockpit. So we'll see how it handles all 7 or 8 of those. So you'll need to make sure that these ports are set up to be accessible on your computer. So if you go into Windows Firewall, make sure that the Web API port is on the inbound rules. If you go to the protocol and ports, I just set those ports and said that they're allowed. And that should allow incoming connections on those ports. I don't think you need to do it on outbound. You also shouldn't have to do it on your router because it's not going outside of your local network, but your own network will be the decider on that, and you might have to make some adjustments. If you go to Axes and O's website, on the downloads page, the near the top, he gives you a troubleshooting guide on for networking. So that's a thing that I would pay attention to if you're having trouble getting a connection. In order to test the connection, what you should do is scroll down on this page. There's a lot of stuff here for connecting stream decks and so on and so forth. But I just grabbed this WebAPI API example, the poor man's touch portal. I just grabbed this little button example and downloaded it, and you put it inside of the Lorby folder. And so in my documents, Lorby Access NO files, there is a web pages folder, and so we can show you here. And so there's web pages, button example, and I just put the information in there. So you get this button example folder from that download. And so I just threw that into the documents folder for Access and O's that gets created when it's installed. Once that's installed, you can then go to that address and it'll load. Now, right now, I don't have the sim running, but these buttons would load with information from the simulator, and you can click on them to turn on your lights or your strobe lights, or even manage your autopilot through these buttons. So this just helps you know whether you have things working. And so what you'll need to do is go to another computer or on your iPad or whatever on your Wi-Fi network and access this address and make sure you can access it. Because if you can't access it on another device in your network, then the Arduino is not going to be able to access it either. And that's going to be headache number one. So you'll need to make sure that you get that WebIP set up, or the Web API set up as it relates to accessing. So now let's talk about some of the hardware that I use. So we'll start with this Qualia display. So this is a 2.1 inch, or this is actually the ESP32. So it's $20 currently. And this is the board. It has the Wi-Fi built in, and you just plug in USB-C in the bottom and you're off and running. You don't have to do any wiring to this Arduino at all. So it's kind of nice as a project. You don't have to be an electrician here to figure out how to solder and wire or any of that kind of stuff. The display that you see connected is this display that I used, which is the no touchscreen version. And it's currently $25. So that display just plugs into that connector right there, and once you've got it plugged into power with USB-C, then you're off and running. Now, to get this to do stuff in the sim, now of course you can just display information, but in my case I'm using an encoder, and you could use anything on your joysticks or whatever you currently have. But if you wanted to custom build a panel for this and have it all connected, as I'll show you in a bit with the Fusion project, then you're going to need some way of getting that encoder dial to connect to your PC. And this button box interface from Leo Bodner is what I use. I have 3 of these in my current cockpit, and they do 64 buttons a piece, and you can pair together lines for encoders. So this is a really handy device if you want to. It's just USB connection in the back, and you can actually use simple plug connections here between your encoder and this board. You don't have to do any soldering or anything like that if you don't want to. This is the project on GitHub that I've got linked below in the description. It's got a folder for the Arduino project that includes encoded versions of the images that you use. We'll talk about that in a bit. And it's also got some of the original pictures that I did convert with. And I think that's it for like the basic hardware. When we talk about the physical object in Fusion, let me bring that project up. So this is in that GitHub project. It's a Fusion file, so you'd need access to Autodesk Fusion. When you open that, you'll see what's here. And so what I've done is I've modeled a stand-in version of the display, a stand-in version of the ESP32 in green there. And then I have a front part with 3 encoder wheels that you can use to do pressure, altitude, and maybe heading or something like that, or vertical velocity if you're trying to do something like the PC12 where it has that knob for the altitude selector, and you can use the push button on your encoder to switch between managing velocity and vertical velocity and your altitude. And so I've modeled kind of stand-in versions of those. As it relates to what encoders I used, I just went to Amazon and I bought a pack of 10 of these for $12. And so that's the encoder that is in the Fusion file, and it's what I used. And there's just 3 little wires that you end up connecting to your Leo Bodner card. The center one's ground, and then the outer 2 pins are your 2 buttons for going left and right. On the back side are 2 pins for the push button. One of them is a ground, and the other one is for the button actuation. So now what I've done is I've opened up the Arduino code in the Arduino IDE. And I figured this is kind of useful to go through to talk about how does it even work, and so you can get a sense for what's necessary and what's covered in the project as it relates to the code. So I originally got this idea from a user named Tanarg on the DCS forums. He posted how to use these displays for a radar altimeter, and I then said, well, I can do most anything with that, and took that idea and then learned how to use Access NOs. So in the comments here, I talk about what hardware you need, and then some code that you can, some scripts you can use in Access NOs, and I'll show what that looks like in a minute. So these are your increase and decrease scripts for Access NOs. In this code, I actually do error handling using the barometric pressure, because your little history fact for today is the fact that the highest pressure recorded was 32.01 inches of mercury. That was in Siberia in 1968. So that means that those 4 digits you can use a lot that make no sense within the airplane, but could make sense as it relates to debugging this. And so I use different codes. And so if you see something like 3333, that means the connection to AAO works, the sim is working. It's just you don't have a plane loaded, and most likely if you look at Access NOs, it'll say waiting for aircraft. So that barometric number will change depending on what problem you have. Some of these are kind of like fatal errors. That means that something's not working at all. Down here, no Wi-Fi. If you get 999, then you know you have no Wi-Fi, so you got to fix your Wi-Fi setup. So as we scroll through, we include some libraries for dealing with Wi-Fi setup and the Wi-Fi password. I give you some global variables that we work with. Mostly it's just altitude and air pressure. And then we bring in a library for Arduino graphics library. What this does is this allows you to actually send images to those displays. So these next sections are just setting up those displays that I showed you on that website and getting the settings right for those displays, so that way you can send an image to them. The next library that we use is TFT ESPI, and all we use this for is just for moving the images around, rotating, making a needle that spins around, or the altitude bug. And so we just have to create little images that we assemble together to make a single image that we then push using Arduino graphics library. And so in this, you'll see some functions. This first function is getting digits from the values, because in my F18 situation, I've got, a 10,000 and 1,000 altitude. I've got the four pressure values. You could change this, of course, to your own style if you want. You can even use the Arduino graphics library to draw your own stuff, if I understand right, or maybe even with this TFT sprite library, you might be able to draw your own things with it. And so then I have another function for moving the 10,000 and 1,000 numbers for altitude, moving the digits for barometric pressure, and this is the function that actually draws the screen. And so what you'll see is we have to pass it an altitude, a pressure, and what angle the bug is at. And then what we do is we work our way through and we assemble that image, starting with the background, and then we add the large vertical numbers, the small vertical numbers, and then the gauge face. The gauge face has transparency to let those numbers be seen. So that was important. It's a transparent PNG that I ended up converting. And then the needle angle, we have to get that needle angle for rotating the altitude needle, and the same thing for the bug is that we push a rotated version of it to the screen. Down here, this get data function, this actually does all the work with access and O's. So it basically, we're already connected to Wi-Fi at this point, and then we just create like a network connection, an HTTP connection, and then we have to formulate what's called a JSON document for a JSON request. And in here, you can see I'm asking for some sim variables, altitude, pressure, and a kind of a custom variable in access and O's. I'll show you how to do that in a bit. A custom variable for this altitude bug that we're doing. So we need those variables. We also want the title of the airplane. We don't really use the title of the airplane here other than checking whether the airplane is loaded or not. But in the code, there's a spot for you to do airplane specific stuff. And where this will be really useful, as you can imagine, I mean, a radar altimeter is actually might be more related. In the Learjet, I know the little marker for the radar altimeter, that uses a different variable than the standard variable because of how the dev did it. So if you have airplanes that just kind of have different approaches to doing stuff, then you can use the title of the airplane, so you can do some code switching in here. So down here, we start creating that JSON request. We do or create a request for it and put in that request. And you can see here I start doing the error checking in the sense of, okay, well, we didn't get a deserialized result, so we can go with this 4444 error. If we don't have that, then we move on and we start digging the information out. So we dig out the altitude, the pressure. We convert the pressure because it comes to us in a different value. It has a decimal value, and I just want the first 4 digits because that's all that's needed. So I multiply it by 100 to move the decimal place over, and then I round it off so that way it's just a 4-digit number. Down here, we get the current bug altitude, and that's measured in feet, right? Because you're setting a foot value. I want to be at 750 feet for my decision height or something like that, or 200 feet or whatever it may be. And since that's in feet, but we need that in degrees, we do a mapping and we map it from feet to degrees. So that way it can be rotated correctly. And then we do a little bit of error checking here to make sure we're not out of bounds on that. And if we do things right in access and O's, we won't be. As we move down, this is the example of how you could do some aircraft code and check on the name of an airplane and, and do custom code in it if you really wanted to. And then we go down here. This is the setup function. All Arduino programs have it. So this is where you set up stuff. You can see I set up the Wi-Fi. I set up some of the graphics stuff and get some of those images set up that you only have to do once. And then down here, I did some performance testing. It seems like it takes about 179 milliseconds for the little Arduino to assemble all these images and put them together as a picture and get them on the screen. So that means that's as fast as it's going to go. And at least with this implementation, someone who's probably a professional programmer might be able to do better than what I've done. But so at that rate, you know, you're looking at 5 frames a second if you set it to about 200 milliseconds, which is also the recommendation from Access NOs as it relates to a frequency of getting an update. It's not that big of a deal for Altimeter since it's a lagging instrument and doesn't need probably faster than that. The bigger issue is just the visual appearance. You know, 5 frames a second, if it's moving really fast, it can get jumpy. The needle will jump around. And doesn't move smoothly. But again, you know, most of the time in the airplane you're looking at it, those things are not moving that quickly. And so I just haven't found it to be a big issue. And so you can see here that I've set the delay between each request of that data to be 200 milliseconds, just so that way we're not pounding the PC a lot, especially once you imagine you get 9 of these going, each asking 5 times a second for their data. You know, that could be a lot. And so we're just trying to make sure that we manage our workload there. Okay, so in this last bit, we just go back to Access NOs and kind of just look at how we get this all working together. So you can see that I have 2 binds here for the Pilatus altitude bug increase and decrease. If I double click on that one, you'll see that it's running a script. And so every time that button 59 is pressed, it'll run this script once. So let's go to those scripts and look at the script editor. So here's the script editor and there's the script. It's the altitude bug increase script. So I had to create a variable to hold what that setting is in Access NOs. And so to do that, you go to scripting, input custom variables manually, and then this little window pops up. You can choose what kind of variable you want to do. I did an L variable. And I always preface my variables that I intend to be just kind of internal to Access NOs as AAO variables. And then I'll give it a name and what it is. It's a number, it's a string, you know, it's a degree measurement or, you know, whatever that may be, because L variables have units. You can put a description there and then you can choose, you know, maybe what airplane, if you want to group it by that kind of thing. So you create your variable name there, and that variable that I created was AAO underscore altitude underscore bug. And that's an L variable. When you refer to internal variables in Access NOs, you don't have to put its type. So normally when you're talking with an L variable, let's say this was a number, in Microsoft Flight Simulator, you'd put a comma here and then you'd write the word number. You would need a unit here because Microsoft Flight Simulator, every L variable has a unit and you need to know what unit you're dealing with, because there's actually unit conversion and such that can go on. But with an internal variable with Access NOs, you don't need that. You'll see that right now I'm doing an increment of 25 feet every time the button is pressed. I don't feel like I need much more detail than that. That'll get me most values that I need for a bug like that, but you can change it here. You can make it 10 feet, 1 foot. It depends how many times you want to spin the little encoder wheel. And then because I'm doing 25, it only makes sense to go up to 975 feet because the next increment would be back to 0 again on the altimeter. So I just set a maximum there and say, hey, if I'm at the maximum, the next time just wrap it around and make it a 0. So that way the bug spins in a circle like you would expect. And otherwise, what I do is I take 25 and add it to the value, and I stuff it into the value to update it. Decrease looks the same. The only difference is instead of 975, I'm checking for 0. So now you could imagine if you're at 25 feet and you spin to the left or counterclockwise, then you need to pass through 0 to the 900s. So if you're already at 0, then and you spin it, then what it'll do is it'll just set the value to 975 and continue counting down from there. I guess you could probably change this from equal to be, less than or equal to in case you somehow got into weird negative numbers or something. I don't know, but so far this worked for me. I haven't had any issues with this approach with what I'm doing there. So those are the little scripts that you target in your bindings for axis and O's. And all that's left is, 3D printing all the material, the hardware, and putting it all together. One of the things that I said that I would talk about later is the discussion of the altitude bug for the PC-12 inside the sim. There is a bug there that you can grab with your mouse and you can drag it around the altimeter there. And it would be nice if that altimeter bug matched the bug that's on your little screen, just so that way your real physical world matches what's in the sim. The problem that I ran into on that particular example is that I couldn't figure out their L variable. They've got some really weird. It's not just, it moves in small increments, looks like 3.6 degrees per jump, but the value of the L variable isn't connected necessarily to the animation of that bug. And so they might have another variable that I haven't found yet by digging through their code to connect that L variable to the actual animation, because changing the L variable, while I could do that with axis and O's using the script here, you would do it in your bug increase and decrease scripts. It didn't do anything to move it in the sim, and that's just because that value and the animation of it are disconnected from their code. And so in that case, it doesn't work out. Later, I'll be doing an example of a radar altimeter, and in particular of the Learjet 35A. And in that case, FlySimware's approach, the L variable that you use there will manipulate that little bug, and so the two will synchronize, and there'll be a slight modification to these scripts that we use here. The reason why we won't, you could technically do that per plane stuff inside the Arduino code and then send that back to axis and O's, but that's a whole nother internet request that I don't think is really useful as it relates to the horsepower of that little ESP32, and you'd rather process it on your PC, and it's just another connection that's got to go to axis and O's. So you want to try and keep that down as much as possible so you get the most performance. The last thing that I said that I would come back to is dealing with those little pictures that you see on the display. So, you can use Photoshop to create your images and things like that, but at the end you have to convert them to code that can be understood in the Arduino project. So in this case, if we look at the face of the altimeter, it gets converted, and you can actually see, how it's converted into this ASCII representation of the image. Well, actually not. This isn't the ASCII. This is a preview that's generated by the app that I'm about to show you. Down here is the actual code that is the value of the image that is read by the Arduino project. So in this case, I'm using an app called LCD Image Converter, and you can just say like if you wanted to start with a new image, but we're not going to really make a new image in here. In fact, instead, we're just going to open an existing image. So let me open one. I'll just grab one. This is an airspeed indicator that I was working on in a separate project. So here is the airspeed indicator. And so if you're going to save this out so that way you can use it in the project, you need to adjust some options. And so if you go under options and hit conversion, there are some tabs, and you can go through and there's all kinds of things that you can change. But the things that you have to pay attention to for this project is that you need to use little endian byte order. So that's a switch you would have to make sure it's not on big endian, but it's on little endian. So that's important. And then up at the top, the preset. So there are different color presets. And then the color preset you will use is R5G6B5. And so that is the preset for how it exports it. So those are really the only two big change. Oh, and then the block size, 16-bit block size. So three things: block size, byte order is little endian, and then the preset is that R5G6B5. Once you do that, then you can export this out. And so and then you hit convert, and then it'll convert it, and it'll create the .h file that you need for your project. And that .h file will look like this. And then you can use what's here as an example. I cleaned it up. It has some extra bits in it that you don't need for the Arduino project, and so creating the array and things like that up here, I clean that up. And you can see how I've done that for this bug one. There's no extra information here. I did not do that for the gauge face. At least I didn't get rid of this preview, this ASCII preview. It's all ignored by the app anyways because it's commented out. But I did get rid of the other parts of that or extra from the conversion process. So that just shows you how to convert an image so you can do your own custom images if you wanted to.